How does deep learning work? The current approach. A deep network is a network with many layers. These networks are commonly used to perform classification tasks on images. The image is processed through the network until it reaches the output layer and selects the correct output. But how does it work? The common explanation is that as the image is processed through the network, deeper features and features of features are recovered as it progresses. Yet, those features and feature of features are not well defined. So how does deep learning actually work? What is the mechanism that makes it so successful? Let's present a new approach to deep learning. Let's see how deep learning classifies a set of labels, which we will denote as numbers. The network is comprised of many layers, specifically n layers, from input to output. If we look inside each one of the layers, we will see that they are comprised of many filters. But what role does a single filter play? Assume input of type 1 is presented to the system. Each filter recognizes a different small set of labels. As the layers progress, the recognition of those labels is enhanced. But how can those filters recognize a specific label? The proposed new mechanism answers this question. At layer n, among the 500 filters, 150 are label 1 filters, and 350 are not. Each one of the 150 filters have label 1 among their set of 3 labels. Each one of the 150 filters contribute to the output label 1. A total of 150. The rest of 2 labels of each filter contribute on average a small noise on the other output units. The rest of the 350 non-label 1 filters contribute a small noise on each output unit. This enables the network to recognize a specific input. The new understanding can also greatly optimize the network. For instance, using the insight of single filter performance, one can remove a significant number of filters without affecting the overall accuracy. Another way to reduce complexity while maintaining accuracy is to apply filters cluster connections. We look at a single filter. Each filter is connected to all output units via weights. Using the knowledge of the cluster of each filter, we can dilute the weights that do not belong to that filter's cluster. This allows each filter to contribute to the output while greatly lowering the number of needed weights. In conclusion, each filter recognizes a small set of labels. The recognition becomes sharper as the layers progress. This is the underlying mechanism of successful deep learning. And most importantly, this mechanism is well defined, in contrast to the feature language, which is not. This new understanding can lead to real-world applications. Without reducing the overall accuracy, one can dilute the number of filters, lower the number of layers in the system, also significantly reduce the number of weights in the system. This can greatly improve latency times, as well as memory usage and complexity while keeping the network's capabilities. To learn more about this new mechanism, see our published articles.